On today's program, we're going to learn more about CST technology, and our speaker is Bill Livoti. Bill, welcome to our program.
Thanks, Jim. It's good to be here. Today we're going to discuss an alternate solution for circulating water pumping applications. This technology is called Controlled Start Transmission, otherwise known as CST. Just an overview of the power industry and this particular application. The startup and shutdown sequence of a vertical, single-stage, high-horsepower, low-speed circulating water pump in any power plant, be it coal or combined cycle, is very harsh on the pump itself, as well as the associated prime movers and supporting structure. Most power plant operators have a tendency to start and stop frequently the circ water system and cycle the power plant. This is most prevalent in combined cycle pumping applications. The majority of domestic fossil power plants were constructed in the 1960s and 70s. But with the new legislation pending and implemented legislation, they're going to have to adapt to the climate change regulations as well as those legislations legislated by the EPA. Because these regulations, power producers will be forced to take a new look at their existing circ water pumping systems, both for efficiency gains as well as improved reliability. This presentation will discuss a new approach using a proven technology to provide the power plant operators the reduced operating cost as well as the improved pumping system efficiency. Additional current situation of the power industry: the average age of a North American fossil power plant is 40 plus years. Plants are operating differently than their original design. There's more starts and stops, as I mentioned earlier, mostly in combined cycle power plant applications, but some coal plants are cycling their loads, not necessarily starting and stopping, but they are modulating the loads. Additionally, the existing plants are looking for increased capacity, as well as improved heat rates. Motors, for example, are being subjected to environmental and weather conditions, as well as multiple rewinds. Again, the legislation we mentioned, specifically 316B, the Clean Water Act. Additionally, water is becoming more scarce. States are becoming more resistant to giving proposed power plants water permits. And then you also have the increased parasitic load due to the environmental controls being legislated for the fossil power plants. Also, original motor OEMs may no longer exist. Therefore, that replacement motor isn't available. Additionally, motor base plate and intake structures have degraded over time, impacting alignment and possible pipe stress. We'll discuss the root cause of this momentarily. Let's review the basic, typical circulating water pump flow process. So the water, if you look to the left of the schematic, the water is originating from an estuary, be it an ocean, river, stream, lake, passing across a traveling screen into the suction of the pump, out the discharge of the pump across the MOV, that's item number 3, into the condenser, through the condenser, and then you have at the discharge of the condenser a control valve to control the flow. Exiting the condenser, the water enters the cooling tower. As it exits the cooling tower, it goes back through water treatment facility and then ultimately back to the estuary. That's your basic, typical circ water pump flow diagram. So in this diagram, the operating considerations in a circ water pumping application, as we outlined, is the conventional flow process and startup methodology. during the startup sequence, the pump is started against a closed discharge valve. As the pump is energized, the discharge valve slowly opens. During this sequencing, the pump goes through a very abnormal cycle. The flow is being restricted in the pump, resulting in internal recirculation, and the pump is shaking and shuddering during this process, causing excessive vibration and stress on the pump, the motor, the intake structure, the piping hangers and supports, as well as the valve. This startup sequence is only intended for a very short period of time during this duration. However, in some configurations, this startup duration may last for 15 to 20 to 45 minutes in some cases. By maintaining that closed or partially open valve for these longer periods of time, it is likely that there's going to be unavoidable damage to the pump and system. Additionally, if the discharge valve, typically this is an MOV, fails to open or opens too quickly, the system will not be properly ventilated, resulting in water hammer. This anomaly will also result in severe damage to the pump and system. So our solution to this particular application is a large horsepower, low-speed gear motor. Large meaning above 1,000 horsepower and above, utilizing an AC 4-pole induction motor, as well as a planetary gearbox comprised of a single-stage reduction with a hydroviscous clutch for a controlled startup and shutdown. This technology was originated years ago within our company for conveyor applications where these are very long conveyors, primarily in the mining industry. It's an electromechanical device that provides a controlled start of the output shaft, which is coupled to a conveyor pulley achieved by slipping a hydroviscous wet clutch. The motor speed is reduced via a gear reducer, primarily used to drive underground and above-ground conveyors over miles of distance, and again, as I said, typically in a mining industry. A little bit of the history. The CST technology for planetary gearing utilizes a proven technology by the Dodge Power Transmission Division of Baldor ABB. The technology was originally introduced in the 1970s. This is where the control start transmission originated. In 1981, we introduced the wet clutch technology. We currently have over 2,000 CSTs in operation, ranging up to 2,500 horsepower. The top 3 coal mines in the U.S., top 7 coal mines in China, and the top 6 coal mines in Australia utilize the CST technology exclusively. A little bit on the CST gear motor functionality. It comprises a soft start. This is called an electromechanical soft start. This allows the motor to start unloaded. The load is then accelerated at whatever rate is desired, providing a stable speed control via the wet clutch. We also provide a fast response control system. This is a standard communications connectivity. The system inherently is torque limiting with an overload protection, and the pump speed regulation is possible by slipping that hydroviscous clutch. The gear ratio selected is based on optimizing the pump speed to provide efficient operation, meaning we will design the gearing to hit the optimum speed of the pump to achieve best efficiency point. The electromechanical soft start minimizes the impact on the power system, thus lowering the duration of inrush current during the acceleration of the pump, and this is significant. We also provide extended acceleration-deceleration times utilizing the soft start methodology. This also provides increased motor life and allows for repeated starts without restarting the motor, as the motor is disconnected from the clutch through the hydroviscous clutch. We also provide a 4-pole motor as opposed to a high pole count motor. Using a standard 4-pole motor and the gearbox, we could provide whatever speed the end user is required for their application. The 4-pole motor provides lower motor cost, better motor availability, smaller and lighter reduced mass, and higher efficiency and power factors, as well as reduced voltage, or full load amps, I should say. A little bit about how the system reacts relative to your current configuration, and then we'll discuss how it is impacted with the CST gear motor solution. Some of the system issues out there are high condenser back pressure. There are situations where you'll have reduced net positive suction head. There's increased plant load. You are committed to a fixed speed application in your current design, and then also process control. All of these issues impact where the pump operating point lies relative to the system curve. System curve uncertainty results in uncertain pump operation, therefore impacting the pump reliability and efficiency. The screenshot you're looking at is showing a system curve with 3 load points laid over the pump curve. And you can see where the red 0 is, the circle, we're showing the specified operating point. And the 2 points where the flames are burning the dollars, we're showing you on the left of your screen where the pump is getting pushed back on the curve in the case of high condenser back pressure. The pump is being forced back on the curve. At the right, that's where the pump is running to the right of the curve and away from its best efficiency point. In both cases, this results in reduced efficiency, higher operating cost, and reduced reliability. The typical circulating water pump utilizes what they call a mixed flow impeller. And the image on your right is showing a basic 3D model of a typical mixed flow impeller. Mixed flow impellers utilize both centrifugal force and lifting force action to move the water. And you can see by the horizontal arrow and the vertical arrow, we're showing where the water is discharged both radially and axially into the volute casing. The orange coloring on the impeller denotes high velocity fluid flow, and the blue is showing lower velocity at the exit of the impeller to the discharge of the pump. Now, what does that look like on the pump curve? Here's a typical mixed flow pump curve. And you can see the red line is your head and flow, the green line is your brake horsepower, and the blue line is your efficiency. And you will note that where the lines intersect, where the blue line and the red line intersect, is the pump's best efficiency point. And you'll note as you move to either to the left or the right, your efficiency begins to drop dramatically. You will also note how the brake horsepower rises at shutoff, then drops a little bit, then rises to the best efficiency point, and then begins to drop off as you move to the right of the curve to the runout condition. This is significant. This is why it is so important to maintain best efficiency point of your pumping system. The typical circ water pump system is what they call a friction-dominated system. Friction-dominated system, and it means that there's little to no resistance at the discharge of the pump. That is why a circ water pump is started against a closed discharge valve. Now, during the startup process of a pump in a friction-dominated system, again, you have no resistance at the discharge. So the pump must be throttled to maintain control. If the pump were not throttled, it would run out to the right of the curve and the motor would trip on high amps. With the controlled start methodology, we are able to control the speed of the pump and bring the pump up without overloading and creating recirculation within the pump by slipping the clutch and controlling the speed of the pump. And you'll note, by doing so, as we ramp up the pump, following the red system curve line, you will see that the pump maintains its best efficiency point throughout the startup process. So, by maintaining that efficiency, it means reliability. Efficiency and reliability complement one another. This screenshot is showing the Behringer curve. It's named for a gentleman named Paul Behringer, who is one of the foremost authorities on pump reliability. In his diagram here, he's showing you a bell curve. In the center is a vertical line, green dotted line. That is your best efficiency point. And what he's demonstrating here is as you move away, looking at the bottom of the bell curve, away from BEP, your reliability drops off dramatically. The closer you stay to best efficiency point, the greater your reliability. Now the effects, we were talking about starting this circ water pump against a closed or partially opened discharge valve. How does that impact the pump performance and reliability and the load? Well, this next slide is going to show the effects of a control valve. And again, you will note, here's your system curve, that's the red line, the pump curve is a blue line. Now, let's look at the next screenshot, and you can see as that valve is throttled, you're pushing the pump back on the curve. And the more that pump is throttled, the further it moves back on the curve, loading up the pump, causing internal recirculation, high vibration, and shaking the intake structure in the motor. And further, you're also wasting energy. So the specifications of our CST gear drive design, let's review the specifications specifically for a pumping application. In general, the technology specification for the CST gear motor in a pumping application entails a planetary configuration with concentric input and output shafts. The control start feature is incorporated by a hydroviscous internal wet clutch. This controls the pump speed and flow, thus enhancing the pump system startup. The technology is suitable for vertical shaft operation with the output shaft down. It's flange mounted to the prime mover and driven equipment. The reducer flange is doweled to the motor base. There's a male register for the driven equipment side. This allows for alignment to the pumps. The CST input shaft is coupled to the motor with a splined coupling. This eliminates the need to do an alignment. So they are automatically aligned. They're doweled into place and aligned and coupled with the splined coupling. The unit rating is based on the minimum rating component of the gears, shafts, keys, etc. The drive is designed to accommodate momentary peak loads up to 200% of the unit rating. The maximum design operating temperature is around 200 degrees F per AGMA 6023. Here is a three-dimensional image of a typical CST gear motor. Now, this next image we're showing you the output shaft. The output shaft is where the rigid coupling would connect the CST to the pump. Here's a cross-section of just the CST gearbox, and we'll go into more details momentarily on how this functions. Now, we're going to show you an actual live interactive video of how the CST gear motor is assembled. What we're looking at now is the Kingsbury thrust bearing going into the bottom of the gearbox. Now you have your sun gears, your planetary gearing, your pins holding your gearing into place. Now your shafting, and that's your spline coupling. Now your sun gear, and these are your stationary and rotating clutch plates, and we'll go into more of that detail momentarily. There's your retainer for the clutch. Now we're assembling the components, bolting it together. That's your dry sump. We do not utilize a seal. That's a dry sump. Now we're going to assemble the motor onto the CST, and you'll note that that just drops into place. There's no alignment required. The only alignment required on this technology is aligning the CST gear motor to the pump. And now we're adding the ventilation for the 4-pole motor. So that's basically the assembly of the CST gear motor. So further to the specification and design of the gearing component, it's a planetary gearing arrangement, divides power into 3 paths: high power density, high efficiency, and load sharing through floating sun pinion and ring gear. And this is with the clutch option only. The double helical type gearing is utilized for lower noise and vibration. Additionally, there is great effort made to make this a compact height to minimize the overall height of this solution. The materials and quality, the sun pinion and planet gears are grade 2 carburized steel. Steel is carburized, hardened, and ground. It's to AGMA Q11 quality level. The ring gear is a high alloy grade 2 hardened steel to AGMA Q9 minimum quality level. All material will meet ANSI 2301 cleanliness specifications. The bearings life calculations are per bearing manufacturer catalog methodology. The planet bearings are a cylindrical roller with a minimum unadjusted design L10 life of 50,000 hours at the motor rating power. Thrust loads are supported by a spherical roller thrust bearing L10 life of 100,000 hours at a 36,000 pound of external thrust. I might also add that we also use a Kingsbury thrust bearing, as you noticed in our 3D model. Depending on what your thrust loads are, we will meet the required thrust. The design is for 50,000 pounds of maximum momentary down thrust. That's our basic design. We will meet whatever down thrust your application requires. And again, as I mentioned, we also provide a Kingsbury type thrust bearing. The housing and carrier is a rigid welded steel fabrication. The planet carrier is integral output shaft, is a high alloy steel forging. Again, as I mentioned earlier, we use a dry well as a positive method for preventing oil leaks for the output shaft seal. The output shaft also has a dual lip seal as a backup and excluder device. The seal material is Viton or HNBR, and the input motor flange is sealed with a liquid sealant. The lubrication is a combination of splash, dip, or pressure feed, depending on the location. Acceptable lubricants will be an R&O mineral type oil. The viscosity selection is based on your ambient temperature. We utilize an internal pump with filter to pressure lube the upper bearings and the gearing. And the oil level is established by a sight gauge, and we also utilize a magnetic drain plug to capture metallic particulate matter. Testing and documentation is a full load test for 4 hours in our Advanced Development Lab in Greenville, South Carolina, and we provide one paper copy each of the installation IOM manual as well as certified dimension sheets. We will certainly make more available per your request. All of the CST gear motors are modeled using FEA to ensure that we do not have a natural frequency or any other design issues. Let's discuss the CST operation. The design incorporates, as I mentioned, an integral wet clutch design. The torque is transmitted by varying pressure to actuating piston via a pressure valve and an electronic motion controller. We'll go through this in a moment using an interactive video similar to the assembly video. The motor-driven gear pump for the clutch piston is used for the actuation of said piston. Cooling oil is through a pump and heat exchanger with a reservoir. We utilize an electric motor-driven centrifugal pump which circulates the clutch cooling oil. The cooling oil is pumped through a unique pattern in the friction plates during acceleration, and we'll show you an image of these clutch plates in just a moment. The cooling oil flow may be turned off when the clutch is completely locked, and the pump will do this automatically. Externally mounted water or air-to-oil heat exchanger is used to cool the clutch pack. The reducer housing is used as the cooling oil sump. As we mentioned, here's an image of the clutch plates. If you look at the black arrow, that's overlaid on top of the actuator piston. That actuator piston is forced in by the positive displacement pump, engaging the clutch plates, and thus engaging the planetary gearbox driving the pump. If you look to the right of the screen, you'll see the friction plate. That's called the rotating plate. And you'll see the diamond pattern in the plates. In those grooves is where the oil flows, and that creates that film barrier that prevents the plates from contacting. The centrifugal pump is what draws the heat away from those clutch plates, cools it through the heat exchanger, and then sends it back. The lubrication, cooling, actuation, electronic controllers incorporate a motor-driven tandem gear pumps, and they consist of two circuits. There's a clutch actuation system and a lubrication system. The CST cooling system covers, as I mentioned earlier and we discussed, the motor-driven centrifugal pump. There's a filter, pressure switch, temperature switch, and air-to-oil heat exchanger. In the operation process, the motor-driven centrifugal pump is turned on before the gear motor starts up. Half of the flow passes through the heat exchanger. The other half bypasses and goes through the filter. The pressure switch at the gearbox inlet monitors pressure and controls the system permissive to start the gear motor. If pressure falls below the set point at the gear motor, it will not start and an alarm will be sent. A temperature switch monitors oil sump temperature, which turns on the heat exchanger cooling fan. A second set point can be set to shut down the system or send an alarm, depending on what is happening within the system. The electronic controller has programmable start profiles. It communicates using a standard protocols of RS-232, Ethernet, and other methodologies. You also have a human interface using a color touchscreen. The controller monitors temperatures, pressures, pump speed, and motor kilowatts. So now let's look at the CST startup procedure. With the CST startup methodology, the MOV can be fully open, or in some cases they do not want the flow backflowing through the pump, so the MOV could be started closed, at which time, if that is the case, the MOV can be programmed into the CST logic. This would allow the pump speed through the CST clutch to open in unison with the MOV, thus providing a benign start. That being said, as we go through the process, the valve at the discharge of the condenser would be fully open. So now you're starting the motor. The motor is started unloaded. It gets up to speed, at which time you start engaging the CST. Now, you may have your MOV start to open at that point, or it may already be open depending on your particular application. At any rate, the CST begins to apply power to the pump. Now the pump is starting to turn. The unit slowly accelerates. You increase pump speed until the discharge line is packed and stable, at which time you adjust the pump speed to the final desired flow and pressure, and then you monitor the control speed and flow at the DCS. It's that simple. Now let's look at how that process works in real time. Here's your CST. Here's a cross section. Now you see the motor has been energized. The motor is spinning. You notice the output shaft of the CST is not turning yet. So now it's coming up to speed. Now the CST is going to be slowly engaged, and as the sun gear comes around, now you can see the clutch plates are starting to turn yellow. Now they're turning red. Now the clutch is engaged. Now you'll see the output shaft is turning. Now the CST has engaged to the pump, and now the pump is starting to spin, and you bring it up to speed. So in conclusion, we have addressed issues associated with the startup and shutdown sequence. We've reduced high vibration using a control start methodology. We've minimized intake and piping damage, specifically with the control start, eliminating water hammer, and as well as the shutdown, a control shutdown, eliminating deadheading conditions. We've addressed the O&M cost, utilizing a 4-pole motor versus high pole counter synchronous motor. Now, we didn't go into details on this, but many of you well know a 4-pole motor repair is far cheaper than a repair/rewind of a high pole count motor, or certainly a synchronous motor. We have also reduced parasitic load due to reduced full load amps and reduced duration of locked rotor amps. And overall, we have improved the uptime, availability, and reliability of your circ water pumping system.
Okay, well, Bill, you presented us some very interesting information, and I'm going to remind you to look directly into the camera as you speak with Jim, and then he's going to say, I believe we've got some questions for you that I'm going to go to right now. And okay, here's our first question. What are the horsepower ratings for the gear motor technology? Okay,
it's a good question. As I mentioned at the outset, we said 1,000 horsepower and above, so we're going 1,000 to 8,000 horsepower currently.
Okay, great. Then what are the speed ranges?
Currently, we are looking at applications where the output speed does not exceed 700 RPM. What we are looking at is a roughly about a 4-to-1 up to an 8-to-1 turn down. However, I want to remind everyone that we can also utilize a 1200 RPM motor to achieve desired output speeds to make it economical.
Okay, great. What is the maximum torque rating?
We are looking at about 3.5 million inch-pounds.
What is the cost of CST, versus a VFD solution?
All right, that's another good question, and that comes up a lot. And I'm going to have to expand just a bit on that to make sense to everyone. When you're utilizing a medium voltage VFD, you have the initial cost of that VFD, but you also have to consider the installation of the VFD and also a structure to house said VFD. So as you couple all that together, you're looking at a significant cost. Now you look at our technology, and you are looking at a very basic, simple technology that doesn't require any special housing. So at the end of the day, when you compare apples to apples, our solution is roughly 25 to 50% of the cost of a variable frequency drive.
Okay. If I'm interested in this, what modifications would I have to make to incorporate this solution into an existing application?
Oh, that's another good question. It's really quite simple. All you have to do is accommodate the heat exchanger. And that could be set outside, you could set it anywhere. The only modification you have to make is to locate, put in a base to set the heat exchanger. As the CST is integral to the motor, which is sitting on top of the pump. So it's very minor modifications. You won't even need to change your switchgear because, again, we're providing a solution with lower full load amps, so your existing switchgear would be more than adequate.
Okay. When could I see this product in service?
We are currently have one running in our lab in Greenville, South Carolina. It is a unit that we have for demonstration purposes for the EPCs and OEMs as well as end user customers. We have a 1,000 horsepower unit set up in our lab. I might also add that this unit has been modified to be, quote, portable, that we could bring to a pump OEM to set up on their test loop, or we haven't had this request yet, but we could actually bring it out to an end user site and install it on their circ water system.
Okay. All great information, and unfortunately, Bill, that's all the questions we have time for today, but I really want to thank you for your time.
And I thank you very much, Joe.